Thank you for inviting me and for the kind introduction. It's a pleasure really to give this talk and to tell you a little bit about my research interests and results. It's a shame that I cannot be there in person. Actually, I lived in Frankfurt 2 years and I love the city, but due to conflicts with obligations here, I couldn't go. So the title of my talk, as was announced, is the thermodynamics of minds. It sounds a little bit strange, the title, but you will see, or I will try to convince you that it's a framework that we developed, a theoretical framework that we developed in order to address a very concrete problem in neuroscience. Let me start very smoothly. I am in general, I was during the last years especially interested in the problem of distributed computation, and just to motivate at the cartoon level, the problem of distributed computation, as you know, we need to solve in order to survive many time critical problems, and the underlying hardware, for example, and it's not the slowest one, but for example, the neurons, which are at the level of 10, 20 milliseconds, is not enough for performing complex computations. So if we perform the computations like in computer science, let's say in the divide and conquer way, so at the local level, solving different problems and communicating the solutions or interchanging the information of the solution of those local problems, we don't have the time to do this efficiently. And therefore, it was proposed that for many of the computations, in reality, the information processing is extremely distributed, perhaps even at the whole brain level. The idea, as you know, is not new. If we start by the left, even more than 1 century ago, and it's linked to the Nobel Prize of Camillo Golgi and Ramon y Cajal, so the discoverer of the neuron, but they shared very opposite view about what is more relevant. As you know, Ramon y Cajal, which influenced a lot the neuroscience of the last century, was absolutely convinced that the computation was local, even at the microscopic level, at the neuronal level. This is called the neuronal theory. But Camillo Golgi, even if they discovered exactly the same, he was always claiming that the power of the computation, at that time there was not such a word, but the information processing was at the level of the network, so it was a kind of distributed computation. More formally than there were many people, I just here selected my favorite items. Mesulam, perhaps in the framework of psychology, started to talk about networks, brain networks, which are associated with computation in a distributed way in that network, even if he was not a computational person and was not really quantifying those networks or those computations in the networks, he pushed this idea a lot. And empirically, perhaps, and more associated with this workshop, as you know, Marcus Reichel discovered those networks by using neuroimaging techniques like fMRI, and then was, of course, confirmed in different species, not only in humans, and with different techniques, EMG, calcium imaging, and so on, that we can visualize, at least at the level of activity, for different conditions, for example, resting state conditions, but also for task conditions where we perform real computation. We visualize really the existence of those networks, putatively associated with the information processing and showing this distributed aspect. But the main aspect that is interesting for me on this distributed computation, and is cartoonized here, is in reality how this distribution is hierarchically organized. And that is like an orchestra. And we know that in an orchestra, when we play a symphony, we need many different computations, many different players, violins, cellos, etc. And they solve the problem locally, but they have to be in constant communication in order to play a good symphony. And we know that the solution is a hierarchical organization, starting by the director, which is guiding all the instruments, But there are also sub-organizations because we know that the first violin is guiding all the other violins. The first cello is guiding all the other cellos. And they have to fulfill the task and be really supervised and guided by this very hierarchical organization. And the question is, do we have something like that in the brain, or is just a democratic distributed organization? So the key question that I am trying to address here is, how is the hierarchical organization of the brain, if there is any hierarchy at all, and how that change under different situations, different brain states conditions, for example, resting state, task conditions, when we are sleeping or when we are under the effect of psychedelics or when we have a psychiatric disease. The direct way of solving this question actually is not so difficult. I mean, we have to parcellate the brain, of course, and the activity of the brain, and define your favorite measure of interactions, functional interaction. Let's say the most simple would be the correlation. It's not the best. You can use more sophisticated measure like causality measures, Grange causality, and so on, and measure those interactions and try to see if there is a hierarchical organization in that particular graph. The problem, and it's the reason why we created this framework, is that in most of the cases, and if we use a relatively sophisticated, valid functional interaction measurements like Grange causality or transfer entropy, we don't have enough data. And therefore, the key idea that I will try to present here and is associated with thermodynamic, and I will explain during the talk, is the idea of the breaking of the detail balance. What that means is that if we break the balance in the communication, in the information transfer between the different participants, we can tell something about the hierarchical organization without measuring explicitly the functional interaction. So it's a way of saying something about the hierarchy without measuring the functional interaction. And I will try to show during the next slides that this is strongly associated with the thermodynamic future of a physical system, which is the arrow of time. So that the system showing a breaking of the detail balance is also showing an arrow of time, is meaning that the system is irreversible. And just by characterizing the reversibility of the time signals that we are measurements in the different conditions, we can say something about the underlying hierarchical organization without measuring the functional interaction. We will do this first in a model-free way, just as a way of analyzing the data. And then we will use even this concept of the arrow of time in order to have some mechanistic underlying understanding of what's going on and what generates that particular hierarchical organization. Before going into that, I mean, I just wanted to show that there are some cases where we can calculate really the functional interaction. That was a paper that we published many years ago using really the large data set, which is the Human Connectome project, where we have the different states, resting state, and 7 different cognitive tasks. And as you know, there are long durations conditions, 2 sessions of the 22 minutes of resting state, many participants. At that time, we use it over 1,000 subjects and so on. And because we have a lot of data and we can calculate our favorite measure of functional interaction, I am not going into detail, this is just to give you a flavor that sometimes it's possible to calculate this functional interaction. And for example, what you see here in those renders, who are at the top of the hierarchy of those functional interactions. Here we use basically transfer entropy, normalize it, and correct it by surrogates and so on. And when you perform the intersection of those top directors in each conditions, you see that there are some commonalities. And we interpreted those commonalities, which are at the top of the hierarchy, as a quantitative practical instantiation of different theories like the global workspace theory of Stan-Dehaene and Jean-Pierre. And we can study quantitatively and base it really on empirical neuroimaging data, the hierarchical organizations and how the hierarchical organization change in different conditions. But as I said, I mean, the main motivation of this talk is that is most of the time not possible, and therefore we use this thermodynamic trick. The thermodynamic trick actually is not new, of course. and was proposed even in a biological context in a very beautiful short book of which is called What is Life from Erwin Schrödinger. As you know, Erwin Schrödinger is very well known because his contribution in physics, especially in quantum physics, but he was extremely interested in biological system. And basically the postulate of the main message of the book is that a living system, a living biological system, is in non-equilibrium. It's in a thermodynamic non-equilibrium, meaning there is an arrow of time. And that's percolated and has a huge influence in molecular system biology since the emergence of that book. But what we are trying to do is to transfer these key ideas to the macroscopic level. So try to use exactly the same ideas, which are not new, but to use that at the macroscopic level, in our case, at the level of whole brain dynamics. What is the key idea? The key idea is cartoonize it here. Sorry for the physicists in the audience. I mean, I will say some trivial things, but I was designing this talk for also for including non-physicists. The key idea is that if we have a physical system, whatever system, in our case will be the brain in a given parcellation, and the units of the system will be what's going on at the level of the parcels. And they are interacting in some way. They interchange information. We know from thermodynamics that if the information is totally balanced, so it's totally symmetric, so we have a democratic system, there is no hierarchical organization at all, it's flat, then we know that the system produces no entropy, the entropy production is zero, and that the system is reversible. So meaning if you watch at the system in the normal direction, in the forward time evolution direction, or in the backward direction, you cannot distinguish that. On the other hand, if you start to generate a hierarchical organization, so you break the symmetry, you break the balance, we say the detail balance in thermodynamics, but you break the symmetry in the information flow, then automatically we know that the system is producing entropy. The entropy production is different from zero, and the system, on the contrary, is irreversible or non-reversible. So meaning that if you observe the time signals in different parts of the system at the local or global level, in the forward direction or in the backward direction, you can distinguish them. So, and that means non-reversibility. And this is the key idea that we use. Just to give you a flavor before we go into the technical details, also for the non-physicists, these are macroscopic systems. On the left, you see a typical non-reversible system. It's a glass of wine, which is shattered by an incoming bullet, which is appear at some point here. And as you see, when you see the video forward or the video backward, you are pretty sure what is reality and what is not the reality. This is the reality, this is not the reality. On the other hand, if you have a reversible macroscopic system, this approximately reversible, and you see these colliding billiard balls, and you see the forward or the backward movie, you cannot distinguish which one is the reality. So if that means that we can say that the underlying system in one case is hierarchically organized, and in the other case is not hierarchically organized. The problem is that in most of the system, it's not so easy as in the two videos that we have seen before to distinguish reversibility of irreversibility. And this is reflected here. On the left side is an excerpt from the movie of Christopher Nolan. By the way, I love Christopher Nolan, but it's the worst movie of Christopher Nolan. But it was perfect for me because there are people traveling forward and backward in time. It's the movie Tenet. And it's very easy. This is like the glass of wine. It's very easy to distinguish who are the guys traveling forward, who are the guys traveling, like in this case, that car, backward. So we don't need a really refined technique to discover the arrow of time or the level of non-reversibility. On the right side, you see a system. It's a physical system. It's not important the details. I took this from a nature physics from the group of Chersinski. It's basically an spin system that by construction is asymmetric. So the information flow is hierarchically organized. The system is asymmetric. That means the system is irreversible. And then I measure here the level of magnetization, some characteristic of the system. And one curve is the forward evolution, the other is the backward evolution. As you see here, you cannot distinguish by eyes who is who. But we know by construction that there is a distinction. And this is what happens in neuroscience, that the signals could show an arrow of time or not, depending if the underlying system is hierarchically organized or not. But the case is not so easy as the Tenet movie or as the glass of wine that we have seen before. Nevertheless, we know that that would be sometimes it's a very easy distinction, but sometimes the distinction is there, but we cannot do this by eye, and therefore we need some refined techniques. And this is what we do in the first approach for solving the problem that we call Tenet on purpose, but is coming from the temporal deep learning network that we use. And the idea is very simple. We have the brain in some state with some measurements. I mean, I will use different type of measure, for example, volt or EEG, intracortical EEG, or whatever you want. Let's say volt. We can measure this at different level, local, network, or even whole brain level. And the key idea is repeated here, cartoonized here, is the evolution forward and backward can be distinguished. So if we have the signals, let's say in one region, can we distinguish the forward from the backward version? And because this could be very difficult, what we do is we train a network, a machine learning black box. And for me, this is the ideal application of a black box, because I don't want to understand why we can distinguish that, because I don't pretend to see the mechanism here. I just want to know if I can separate them. And therefore, I train the network, the classifier. I use a deep learning network with the training data that I know the answer. Okay, I know who is the forward and who is the reversal because I produce this by hand. This is what I measure, and this is what I measure and flip it on purpose. And I know the answer, so that is the supervised learning. And therefore, then if we test this in a cross-validation or in a generalization set, and we see that the classification performance is very high, then we know automatically, quantitatively with the number, which is the performance of this network, that there is non-reversibility, that consequently we have a non-equilibrium system, and what is more important for us is that there is a certain level of hierarchical organization. On the contrary, if it is low, exactly the opposite, meaning that this number is a measure of the degree of democracy of dictatorship, but it's a number that quantifies that in a continuous way. We do that, as I said, we use this Tenet network, a deep learning network that we train with the data, and it will show one case for this approach. We can do this at different level, global network level. I think I will show you first global level and one example of the local level. And we can do this in the whole window or in a sliding window just to have information about the time. This is the first set of results. I will just concentrate on the left panel. What you see here is again the same data set that we used before. It's a large data set. The human cognitive projects, over 1,000 people. I use it more or less 900 for training the network, the Tenet network. And these are the results. Each dot is a participant of the 100 generalization data set. And we see the different conditions, resting, and the different tasks, working memory, language, social, etc. And on the y-axis, what you see is the performance of Tenet, which is a measure of non-reversibility, non-equilibrium, and as I say, important for us, a level of hierarchy. If it would be near zero, means that the system is extremely symmetric, democratic. There is nobody really widening the other regions. If it is one, means that it's really extremely dictatorial. There is one director, and it's basically pushing all the other slaves. And what we see here very nicely is that resting state is hierarchically organized. It's not the most hierarchically organized condition, because when we start to do a task, of course, we need really to break even more the symmetry. We need to use some particular communication channels, I don't know, working memory, prefrontal cortex, and visual cortex, and so on. So meaning that the breaking of the symmetry is stronger, the non-reversibility is stronger, the hierarchy is stronger, and that is properly described with this type of measure. Just another example in a psychiatric context, these are the UCLA database. There are not so many subjects. As you know, as always in psychiatry, the data are not fantastic. And what we see here is, again, at the global level, that is significant differences between different psychiatrical disease like bipolar, attentional deficit, and schizophrenia, and a healthy control group. And when we perform this at the local level, and here we are just showing the rendering results, comparing the different disorder in respect to the healthy condition, we can see who are really disturbing the label or the hierarchical organization. And of course, each of these renders can be interpreted. I do not have the time to do this here, but just to give you a flavor, for example, in attentional deficit, you see that basically the somatomotor cortex is the one which is breaking at most symmetry, is provoking the non-reversibility, and that could be associated with the distraction. That's the external well is distracting us so much that could be associated with the dynamic underlying and computation underlying attentional deficit. Another way of doing exactly the same is the same philosophy, the same conceptual idea, so to associate hierarchy with the arrow of time. But instead of using now machine learning, we use a much more simple measure. And this is what we call inside out. And the idea is extremely simple. Let's see first at the pairwise level, and then we will generalize for all pairs. The key idea is shown here. We just measure the correlation, but not the standard correlation, the shifted correlation. So we shift the signals in these two regions, a value capital T, and of course, then we can optimize this, which is the optimal capital T. And we do this for the forward version of the pair and for the backward version of the pair. And because we are breaking the time symmetry here with this shifting, we can compare the forward and the backward version, and this is what we do here. And by comparing just these two numbers, we have a number which is a quantitative measure for this particular pair of the level of non-reversibility. In other words, if we do this for all pairs, and this is what we do in a matrix where we combine all the pairs, and for each pair we do exactly this difference in the shifted functional connectivity, and at the end of the day, by using the norm of the matrix, comparing the forward version and the reversal version, we have a number at the end of the day which is associated with the non-reversibility, non-equilibrium, in other words, with the hierarchy organization. Just to give you a flavor of this approach, that, as I say, conceptually is identical, but just replace it, the machine learning part, which could be very annoying, by the way, with a very simple measure associated with the shifted correlation. In this case, I use another species, monkey, another methodology. These are EEG, cortical EEG. These are 4 monkeys, different conditions. In this case, I compare resting with different non-conscious conditions. For example, the monkey sleeping or the monkey being anesthetized with different type of drugs. And what you see here on the right side is the main result. Basically, that's for all the trials and all the 4 monkeys, the non-conscious condition is associated with less reversibility, with less non-reversibility, with less non-equilibrium, in other ways, with less hierarchy. And that makes absolutely sense. I mean, if we are not awake the system is much more democratic because it does not need to do or to interchange in a very consequent way information, and we are awake. We have a very significant distinction of the level of hierarchy organization. The same happens with the drugs. When we anesthetize, then the hierarchy goes down. When the effect of the anesthesia disappear, you start to see the recovery going up again. That's happened for all the drugs. The only exception is ketamine, where we see the other way around evolution in the ketamine condition, even if it is used as an anesthetic, as you know, but the level of hierarchy increase and then decrease again during the recovery. And this is probably the reason why ketamine is used nowadays also as a divertiment drug and as an anesthetic. Another example, we are back to humans. We are back to Bolt signals, but in this case, it's a neurological case. There are data from two groups, from Paris and from Liège. In the context of coma, we see the control group, a group with a minimal consciousness state of coma, and a group with a deep coma. And what you see again is really this very significant distinction of the level of hierarchical organization, meaning that the deep coma is associated with really a democratic organization, a more equilibrium organization, and that is the main differences with the healthy group. Last example for the model-free approximation, in particular the inside out, which included because it's probably interesting for you, is an EMG. Again, another technique is humans, and in this case are healthy people, but under the effect of psychedelics. In this case, is LSD. There are many conditions where you hear music, you have the open eyes or closed eyes, you see a video and so on. But in all the conditions, and one can distinguish different aspects, but the only take-home message that I want to transmit here is that in the LSD conditions, basically we have a decreasing of the hierarchical organization. So it's an altered conscious state. But contrary to what is expected, that's okay, it's a super conscious, and well, it's not super consciousness. Or I don't want to talk about consciousness, but it's definitively the hierarchical organization is going down. So it's more like going in the direction of a non-conscious state. In the last part of my talk, I wanted to say a couple of words about the underlying mechanism. So now that we have a quantitative measure, which is going much beyond correlation. I am interested in correlation, and this is what the functional connectivity, as you know, is traditionally doing. I know to know how they are interchanging information, how they are correlated. But now we discover that there is much more information in the hierarchical way, how they are interchanging the information, and we can capture that extremely easy by this thermodynamic idea. Now I can use this in the framework of a model in order to know which are the causes, the mechanistic causes for that. Just let me remember you the basics of a whole brain model, in case that you don't know. The idea of a whole brain model that's nowadays has more than 15 years, practically 20 years tradition, developed by many groups, more or less at the same time. The idea is to use really a whole brain signal data, for example, Bolt data, to use anatomical data to know who is connected with whom, to associate to each node your favorite way of describing the dynamics. That could be very simple, could be noise, could be neuronal noise, could be oscillatory dynamics. And because of the coupling, then you adjust the effectivity of those coupling in order to imitate as much as you can. And at the beginning, we were using all the time the most simple measure, just what we call nowadays the static grand average functional connectivity. So the correlation matrix, nothing else. And then we can optimize the value so that we try to imitate in the model as much as we can what we measure in the reality. This is, I am resuming 20 years of of research in whole brain modeling. But the key idea is to use exactly the same idea, but now instead of characterizing the functional connectivity and try to fit the functional connectivity, we characterize the hierarchical organization. And how we characterize that? In the most simple way, with the difference in the shifted correlation between the forward and backward version. That means with the inside-out approach. But now we try to explain how to generate the measure of this inside-out approach, this characterization of non-reversibility with the model. Here we use, and I'm not going into the detail, a model that was very successful during the last decade, basically, which is a model of oscillators called technically a Hopf model or Stewart-Landau oscillator. And it's a very flexible model and was demonstrated that really can describe many situations at the whole brain level. But now the key difference is that we use this model and we try to adjust really this mass of existing anatomical connection, which is described in terms of TTI, so the so-called structural connectivity. But we optimize now the effectivity of all those existing connections in such a way that we imitate the functional connectivity, it's not shown here, and on top of the functional connectivity, we simulate also the empirical level of non-reversibility, in other words, the hierarchical organization. So just to show what we gain with that, one example only. I use HCP, again, Human Connectome Project. Basically, this is the inside out, so still model free. What we have seen before, basically, but now I put it all the tasks together. And you see again in this approach, a beautiful significant distinction. In that case, I also include data not only from the 3 Tesla equipment, but from the 7 Tesla, and you see exactly the same significant distinction. But I will concentrate now on, I was showing, this is threads and tasks. So this is what we have seen before with Tenet, but now with Inside Out. But I am more interested in the movie, in the watching condition. There is an extra condition, which is not a rest, it's not task, it's people are just passively watching parts of movies. And it's turned out that the inside out, so the level of hierarchical organization, the level of equilibrium, and so on, is smaller respect to rest. And that is a little bit counterintuitive because we have the impression that when we watch a movie, we are doing much more than during rest. And it's not the case. I mean, and probably the confusion comes because of the naming of resting state. Resting state does not mean that the brain is doing nothing. The brain is doing much more during rest than during watching a movie. This is basically the quantitative neuroimaging demonstration that the best way of relax your brain is really to watch. Well, it's not the best, but it's a good way of relax your brain is watching a movie. So we take this difference as an excuse to try to explain this mechanistically, as I told you before. So we infer from the whole brain modeling fitting the non-reversibility level, the hierarchical organization, we infer what we call the GIC. GIC is the Generative Effective Connectivity Matrix. So it's a matrix that has exactly the same topology as the anatomy, but now the values of each of the existing connections is adjusted in such a way, so it's effectively adjusted. So basically, it's like giving a value to the conductivity of each of these fibers connecting two pairs in such a way that we imitate the functional connectivity and the hierarchical organization. And what we see, and in order to prove that really the G contains more information than just the functional connectivity, we use machine learning again to try to classify based on the GIC or based on the functional connectivity if we are watching a movie or if we are at rest. And what you see here in all this confusion matrix and so on, but perhaps I mean the easy way of looking at that is this, that in one condition, if you use the GIC, this is the accuracy of the classification. So you see very high values, 90 something, 97, something like that. For the GIC is also very high for the functional connectivity with much more distribution and dispersion. This is the case of Hollywood movies. They are also showing other type of movies, so boring movies, Creative Commons movies. And in this case, it's really practically functional connectivity cannot distinguish resting from movie, and the jig can distinguish perfectly. Again, I mean, if you distinguish now explicitly, I mean, Hollywood from common creative, so the good movies or the movies with the plot or with the movies without any definite plot, again, functional connectivity is very bad in classifying the state, and the underlying mechanisms explaining the hierarchical organization. So at the end of the day, the explanation of the hierarchical organization is classifying that. Last example on that, which I think is mm, very nice for you because you're interested on psychedelics. We use the data that you know, I'm sure, of Robin Carhart-Harris, basically where he has depressive patients and he has a scanner at the beginning, before the treatment and after treatment, a couple of weeks after that. And there are two arms, one which is treated with psychedelics and the other which are treated basically with the standard pharmacology, in this case, escitalopram for depression. And of course, they have behavioral measurements, symptomatic measurements at the beginning and at the end. We can apply here exactly this philosophy. Basically, we do a model fitting the hierarchical organization, and even more, we characterize the hierarchical organization with another measure, which is more informative, which is called a trophic measure. Which, just to give you a feeling, because I don't have the time to go into the details, is the level of directness. I mean, of course, a very dictatorial system is very direct. There is practically a feed-forward direct information going from the boss to the slaves. In a democracy, the directness is incredibly large because everybody is talking with everybody. And what we see here very nicely is that there is an effect before and after. In both cases, in psilocybin and citalopram treatment, and even if you distinguish who respond and who not responding positively to the treatment, you see basically exactly the same. But the reason why they recover is totally different. You change the hierarchical organization in both cases, but in one case you increase the hierarchical organization and they are fine, or you decrease the hierarchical organization. We studied this in more detail, and what the explanation of this, that here the effects are mainly subcortical and very pretty local, and here is much more distributed. But both are recovering this depressed brain state in different ways, which I think is extremely useful to know and open the world to really to understand what would be the most effective way of changing the disease brain. I just want to finish my talk to give you a flavor that you can use and you can extend all this thermodynamical framework, not only for studying hierarchy, but for study other thermodynamical measurements, which are absolutely interesting. For example, energy consumption. As you know, energy consumption is in computation, not in neuroscience, in really computation, is a problem because we are spending a lot of energy in computation. If I remember well the statistic, there is one global statistic worldwide in 2018, 8 to 12% of the energy consumption, so including everything, cars, planes, meals, etc., was in computation. It's amazing. So meaning that we waste a lot of, or we need a lot of energy for performing computation. On the other hand, we know that the brain is very efficient. And there are numbers. I mean, whether one is consuming 20 watts and the other is consuming like 8 order of magnitude more. And therefore, it's interesting to know something quantitatively about the consumption of energy. There is a thermodynamic relationship, which is shown here. Let me, let me explain each term. The first term, which is in form of the right derivative of time, but forget for the moment the derivative of time, is the entropy of the system. The entropy of the system means how the internal code is changing. This is information processing. So this is the computation that you are performing. And for performing certain computation, if you bring the brain from a state 1 to a state 2, because you are doing something, you are calculating something. So you change the internal code in here and here. This is measured here. And this can be decomposed thermodynamically uh, in two elements. The first element is the so-called entropy production. The entropy production is what we were measuring until now, well, indirectly, but now we can measure directly. It's the best measure of non-reversibility. It's basically just for the specialist, is the Kubler-Leitler information comparing the forward with the backward probability transition matrix. So it's a direct comparison between forward and backward. So it's the best measure of entropy production. The problem is that we could not measure entropy production before in the whole brain system because it's a high dimensional system. And as you know, to measure entropies in a high dimensional system is impossible. But for the moment, let's ignore all these technical problems and say, well, this is the entropy production. So it's the label of hierarchical organization, non-equilibrium, non-reversibility. The second term is the dissipation. So to transform your internal code in order to perform the computation needs non-equilibrium. Therefore, I call this computation in non-equilibrium. And you need to spend some energy that you dissipate to the environment. The key idea, and I don't go into the details, but you can see this in the papers, is that by using a model, we can linearize the model. So basically, we use a model, we use the jig of the model, so what we were using before, and by linearizing the model, in the particular linear case, we can calculate all these three terms explicitly, analytically. And that is fantastic. Just to give you a flavor, and I will use this to perform a comparison of energy consumption and the resting state conditions across species. I will use mice, monkeys, and humans to give you a flavor how the energy consumption in the same condition, which is resting, is changing in all these three species. And then in the context of human cognition, so for the different tasks, we will see how the energy is changing. So just, I am not going to detail. This is the model. This is the Hopf model that we were using in order to find the jig, the anatomy masked effective values, explaining functional connectivity and hierarchical organization. And you can linearize this, and the linear matrix is the so-called Jacobi matrix of this equation. And if you have an equation like this is called an Ornstein-Uhlenbeck equation. And for the Ornstein-Uhlenbeck equation, you can calculate all these entropies that I was putting at the beginning. Why? Because the system starts to get Gaussian and you can solve the Fokker-Plan equation, blah, blah, blah. I'm not going into details. The take-home message is all these three elements that I was showing before, the information processing, so how much costs your computation, the non-equilibrium, and the energy consumption are combination of the things that you were calculating in the model. As you see here appear, well, this is the covariance matrix, this is the diagonal matrix of the noise of the model, this is the Jacobi matrix that I was linearizing before. Meaning there are all things that you know and then you can easily calculate. What you get? In this case, you see the comparison of the energy consumption and the resting state conditions. These are data from Newcastle's. I don't remember. I think there were like 12 monkeys, but some monkeys ran the resting state a couple of times. These are data from Alessandro Gozzi in Italy, mouse, very, very beautiful data, many sessions, long sessions, and so on. And this is HCP in two parcellations, just to show that it's not the problem of the parcellation. And it's the energy consumption per node, so that is normalized for the parcellation. As you see, therefore, it does not matter the parcellation level, it's the same for the human case. But you see, very beautiful that for doing exactly the same, well, we don't know what monkeys and mouse are doing during resting state, but whatever they are doing is costing more energy. So that there is an evolutionary advantage in energetic term in the human case. And this is extremely beautiful. It's my last slide. This is again HCP for resting and all the different tasks, and just concentrate on this left panel. And what you see here is the energy consumption for each different task, but constructed with the fact that the distribution per node of the information processing. So how much you disturb the entropy in the system, in the computation. So for some tasks like working memory, you need really to use and to change many different parts of the brain. For motor, it's very small part of the brain, probably only motor cortex and something else, and so on. And there is a beautiful correlation between those quantities, meaning that the more distributed is the computation, which is this what you are explicitly measuring with this distribution of the information processing, the distribution of this entropy of the system across nodes, across regions. The more distributed is the computation, the most energy cost. And that, of course, can be further interpreted. I don't want to distract you more and leave some space for questions. Basically, the message that I wanted to transmit is that this framework, this thermodynamical framework, that in principle, the intuition is what has, I mean, I don't care about the thermodynamic of the brain. I mean, it's a physical system, of course, I mean, that are thermodynamic effects, but are not interesting from an information point of view. But what I try to show here is that if you formulate appropriately in the context of this idea of the arrow of time that you can characterize very easily through the signals, you can infer how the organization is and how this organization changed in task conditions, in different altered consciousness conditions, sleep, anesthesia, psychedelics, or even in psychiatric condition. And even more, you can study mechanistically what is changing if you are trying to recover the hierarchical organization in disease case. And we started to analyze really also the cost of cognition, the cost of these computations in terms of energetic depths. I finished just acknowledging, I mean, most of the ideas and results that I was showing was developed in cooperation with my dear colleague and good friend from Oxford, Morten Kringelbach. And yeah, thank you very much for your attention.